Namaste. This is Nataraja Pillai. Um, in the hypersonic aerodynamics or hypersonic flow theory, today we will discuss about the hypersonic shock relation. Right? As you know very well that there is a shock wave formation at supersonic Mach number, and even we had a discussion on even the flow is subsonic, right? Maybe zero point 0.6, zero point 0.7 or zero point 0.8. At some point in the flow where there is a possibility of shock wave formation, and that particular Mach number is called the critical Mach number, right? Such definitions we had already. So today we will discuss about the hypersonic shock relations. For your information, the hypersonic shock relations are not very much different from the supersonic shock relations. Say the pressure ratio P2 by P1, ρ2 by ρ1, T2 by T1, or if you consider the other parameters like V2 by V1, U2 by V1, whatever you consider. All these are same, but we consider M infinity tends to infinity and we reduce the equation to hypersonic shock, right? So I acknowledge the hypersonic and high temperature gas dynamics by John D. Anderson. We follow this particular text, right? So let us consider an airplane flying at Mach number 28, right? So the Mach number 28, and it is from the outer region of the Earth's atmosphere, say from the altitude of say 120 kilometers, right? So it is approximately 400,000 feet, right? Now we can say that upon descending into the lower region of the Earth's atmosphere, right, the aircraft need to follow any of these trajectories which we have studied in the last class on this velocity, altitude velocity map, right? So the altitude velocity map we have discussed in the last class, right? So let us see this altitude, say the velocity in the x direction. See here it is velocity, and here you have the altitude, right? Altitude. It is in kilometer, right? This is in kilometer per second. This is in kilometer, and this is in kilometer per second, right? Now, if you consider, in this case, we consider the lifting re-entry from the orbit, right? Okay, then term like kilogram per meter square, it is mentioned where we have studied pounds per feet square. That doesn't matter, right? Now, you see, at any location, right, at any trajectory, right, at any altitude, if you see, the Mach number is really very high. So definitely there is a possibility of formation of the hypersonic phenomenon, and we need to necessarily consider these as a hypersonic flow and the consideration of shock correlation, right? So the purpose of this particular figure is to show that the Mach number is high, and very much high, exceptionally high, right, when it is in the trajectory. So the flight path remains hypersonic over most of its extent, right? Hence, we need to study the fluid dynamic aspects when the Mach number become very large. That is why we discuss the hypersonic shock relations here. Now, let us consider a flow at supersonic flow, right? A wedge is subjected to a supersonic flow, and there is a shock wave created, right? So say it has sufficient high back pressure, right, in the downstream of the shock, so that it can have a standing shock wave, right? Now, um, the shock waves, right? The shock waves considered here are extremely thin. Say here we consider the it is 10 power minus 5 centimeter, right? 10 power minus 5 centimeter, that becomes so small. So, but across the shock, the density, pressure, velocity, the variations are really huge, right? So it becomes very important. So these changes takes place in a continuous fashion within the shock wave, right? So where the viscosity and the thermal conduction are the important mechanism. However, if a macroscopic observer who look into the shock, it is, you know, usually so thin, right? But the observer thinks that there is a discontinuity, right? So therefore, in conventional supersonic aerodynamics, right, shock waves are usually treated as mathematical and physical discontinuity. So let us have an overview where the Mach number from supersonic to hypersonic, there is no dramatic qualitative difference occurs because the shock wave is a shock wave, right? Not like subsonic to supersonic where you have a formation of shock, the phenomenon become entirely different, right? So hypersonic case, the same supersonic exact shock relations can be considered and it can be reduced to the high Mach number. So we can start with the consideration here, right? So let us say um, there is an oblique shock, right, where the flow is in the flow from the left to right, right? So here you have the free stream velocity V infinity, and before shock we call this as 1, and the after shock we call this as 2. Okay. So correspondingly, the Mach number M1 and the P1, ρ1, T1, similarly V2, T2, ρ2, T2, M2, right? So this is theta, right? So theta is a wedge angle, right? Half wedge angle we say, and okay, of course here you have a beta, right? Beta is the shock angle, right? So okay, it is here anyway, right? Now we will consider the pressure ratio. Let us consider. Okay, before that we consider the calorically perfect gas, right? So in the calorically perfect gas, we can have that gamma is equal to Cp by Cv, that is constant. Then the classical results for change across the shock can be discussed, right? Now let us say P2 by P1, right? So P2 by P1 for the supersonic shock, this is equal to 1 plus 2 gamma by gamma plus 1 into m1 square sin square beta minus 1, right? Now let us consider this m1 is large and it goes to infinity, right? So this term, the m1 square sin square beta is very much greater than 1, right? So this equation is now reduced to P2 by P1 is equal to 2 gamma by gamma plus 1 and m1 square sin square beta, right? So now this is the equation or pressure ratio for the hypersonic flow. Similarly, the density, right? So the density consideration is rho 2 by rho 1, that is equal to gamma plus 1 m1 square sin square beta by gamma minus 1 become m1 square sin square beta plus 2. When we consider the m1 tends to infinity, right? So this has become very small when compared to m1 square. Then again this m1 square beta, m1 square sin square beta cancelled, and then we get rho 2 by rho 1 is equal to gamma plus 1 by gamma minus 1, right? Then the next point is the temperature, right? We know from the equation of state that the PV is equal to RT and P is equal to rho RT. We can write the relation T2 by T1 is equal to P2 by T1 by rho 2 by rho 1, where you are familiar with these equations, right? So we can write T2 by T1, right? This is T2 by T1, that is equal to 2 gamma into gamma minus 1 by gamma plus 1 the whole square into m1 square sin square beta, right? Now let us consider the another two components, that is u2 and v2, right? So you know that this is u2, v2, and this is u2. Here we consider u2 and v2 are perpendicular to the free stream velocity v infinity, correct? So this is the free stream velocity v infinity, and we consider u2 as parallel and v2 as perpendicular to the free stream velocity, not perpendicular to the shock wave as usually we consider, right? So we can write the u2 by v1, that is equal to 1 minus 2 into m1 square sin square beta minus 1 by gamma plus 1 m1 square. Now, by having the assumption of m1 tends to infinity for a hypersonic case, this u2 by v1, that is equal to 1 minus 2 sin square beta, right? Because you see, when minus 1 has no significance, then this m1 square get cancelled. This become 2 sin square beta by gamma plus 1. Right? So u2 by v1 reduced to this u2 by v1, that is equal to 1 minus 2 sin square beta by gamma plus 1. Similarly, we can consider the v2, right? v2 by v1, that is equal to 2 m1 square sin square beta minus 1 into cot beta by gamma plus 1 m1 square, right? So we can understand that this equation we can write 2 m1 square sin square beta cot beta, because this 1 has no significance, right? So we can write m1 square sin square beta and cot beta by gamma plus 1 into m1 square. So this finally reduced to 2 sin beta cos beta, right? Because you see this gets cancelled, and here one cos beta by sin beta, right? So this equation, here one sin beta and one sin beta. Now this equation becomes v2 by v1, that is equal to 2 sin 2 beta by gamma plus 1. right? Now, we already know, because somebody asked a question also in the last class, where why there is for a particular theta value, right? The deflection angle theta value, why it corresponds to 2 beta, right? I mean 2 beta value. So we know that one is for a strong shock and another one is for weak shock, right? In our case, we consider the weak shock case, right? Okay, so we go for the next discussion, that is theta beta m relation, right? So um, the traditional theta beta m relation, that is for the supersonic flow, is tan theta is equal to 2 cot beta into m1 square sin square beta minus 1 by m1 square into gamma plus cos 2 beta plus 2, right? So this equation, now we will do an approximation, right? Say, let us consider a small angle approximation. Say here sin beta. So sin beta will become beta, cos 2 beta become 1. Then we consider tan theta approximately equal to sin theta, and we finally make it as theta, right? So with this small angle approximation, we now get the theta as theta is equal to 2 by beta into m1 square beta square minus 1 by m1 square into gamma plus 1 plus 2, right? Here, now let us say that m1 tends to infinity and so on. Say when m1 tends to infinity, so we will consider this, and minus 1 and the plus 2 have no much significance. Then this equation reduces to theta, that is equal to 2 by beta into m1 square beta square by m1 square into gamma plus 1. So here you have an m1 square and m1 square also, then 1 beta here, and we finally arrive to beta by theta, that is equal to gamma plus 1 by 2. So if you substitute the standard gamma is equal to 1.4, then your beta will become 1.2 times of theta, approximately the 20% of change, right? So yes, we had this discussion before. It is very interesting to note that for the flow deflection angle theta, the 15 is equal to theta and this 18 is equal to beta. So this beta is equal to 1.2 times that of theta, right? So, this is just a demonstration, right? Now, okay, so here we will have a summary, right? Say this is a shock wave, and we have started with the upstream as 1 and downstream as 2, and we have a M1, P1, rho 1, T1, and then P2, rho 2, T2, M2. Then we have discussed about P2 by P1, rho 2 by rho 1, and T2 by T1, U2 by V1, and V2 by V1, and beta is equal to gamma plus 1 by 2, or beta by theta is equal to gamma plus 1 by 2, right? So CP we have not discussed. We will discuss the coefficient of pressure calculation for the hypersonic flow, right, in the next class, right? So I stop at this point, and you can also refer to John D. Anderson's hypersonic and high temperature flow. Thank you very much.